thank you for joining. I assume you're here because of the content and not because this room is a little bit warmer than the other room, but I won't fault you if you are. A little bit about myself. My name's Luke. I'm a software engineer at DoorDash. Been there for about 3 years, focused on infrastructure, managing and building new infrastructure, and managing internal access, as with Teleport. So I want to basically walk you through our journey of adopting Teleport to mitigate some of the mentioned Bastion issues, and then talk about some of the learnings that we gained through this process, and hopefully maybe you can use some of those in your own Teleport journeys. So without further ado, a little bit about the agenda here. Want to talk through a little bit of historical context on DoorDash and how we used to manage internal access. Move on to our initial iteration of Teleport at DoorDash and the learnings we got there. Move on after that to the changes we made to our initial setup and how we iterated on our V1. Talk about our tools that we use internally to manage our Teleport setup, and then a little bit about what's next for us in Teleport. Finally, a little Q&A if we have some time. So, a little bit about historical context at DoorDash in terms of internal access and compute. So, historically, we've relied pretty heavily on our Bastion boxes, also known as jump hosts. We use these to access most of our internal systems at DoorDash. Basically, we have a single Bastion instance, which is in our production VPC. We have these peered to all of our peripheral accounts, and we use this for SSH, database, and Kubernetes access. It's managed via Ansible. We have some playbooks to configure groups, install auditing and monitoring systems, and one thing that we do is sync engineering keys to the Bastion so that users can actually SSH in. And we have one instance per environment. So we have a staging Bastion and we have a production Bastion. A lot of pain points here. So obviously it's a single point of failure. So if a Bastion box becomes compromised or we have a malicious user, you can essentially get access to all of our internal systems. Not a great setup, especially in production. We did not have a great fine-grained RBAC setup. We ended up having basically a large admin group who needed to do all sorts of things. So we didn't have a great way to control these individual permissions with our Bastion. Fairly bespoke setup. We had individual EC2 instances managed via Terraform. We, as I mentioned, configured them with Ansible with playbooks that were fairly unmaintained. So there wasn't great ownership there. So kind of not very well understood by a lot of the organization. We required audit logging. Security requirement here, but basically we needed a custom setup to monitor all activity on the Bastions, ship these logs to S3 for processing. So just some overhead there in terms of collecting what people are doing. Another pain point here is the Bastions were required for any Kubernetes administration operations. So basically, if you wanted to exec into a pod, you would need to go to the Bastion. So just not a great workflow for engineers here. Finally, on-call pain points for the teams that owned the Bastion. Basically, if users were running some compute-intensive workload or just dumping a bunch of data to the Bastion, we'd get alerted and we'd have to track people down, tell them to stop doing what they were doing, and clean up the data. So just all around a lot of pain points with the Bastions. So a little bit of context about our compute environments at DoorDash. So primarily EC2, ECS, and Kubernetes. On the EC2 side, apart from our Kubernetes nodes, a lot of our EC2 instances were infrastructure machines. So traffic related, service discovery, secrets management, kind of one-off services. We had a pretty heterogeneous setup, a wide variety of AMIs, no real standard here. And finally, pretty inconsistent access mechanisms. So, as I mentioned, we would use the Bastion primarily, but there were some cases where we just have public instances scoped down to VPN IPs or used Amazon SSM, so just not a very well-controlled access pattern here. On the ECS side, these clusters were pretty much just legacy clusters. We've migrated almost entirely to Kubernetes, but we still have some of these clusters lying around for legacy reasons. They're not very well, I guess the ownership isn't very well defined, and they're infrequently accessed. So when people did need to access these machines, there wasn't a great documented process. And we shared keys for these ECS workloads too, so we just have like a 1-password vault with a bunch of keys in them shared across teams, so just not great practices there. Finally, on the Kubernetes side, clusters were managed, EC2 managed via KOps. Again, we shared keys and configs for admin access and had a custom auth setup. So some of the pain points which I touched on: inconsistent access patterns and shared keys, some not great practices here. No comprehensive RBAC. We really couldn't scope down permissions and really struggled with our large admin groups. And again, no clear ownership. So it was hard to track down owners and really hard to enforce these rules, these access rules. Briefly about user authentication. So on the SSH side, we use public-private key pairs, which were configured in several different ways. As I mentioned, engineers we synced engineer keys to the Bastion, which was one way of accessing our internal systems. But then in some cases, we would configure key pairs via, say, Terraform to configure access to EC2 instances, or use Amazon SSM for access. So a couple different access mechanisms here. On the Kubernetes side, we used DEX and OIDC proxy, which are open source tools for authenticating to Kubernetes, with a custom CLI tool that basically injected authentication data into your kube config so you could access our clusters. Some pain points here, as I mentioned on the SSH side, multiple sources of truth for our keys. Not great to have a repo full of keys and then some Terraform where public keys are managed, and then some, say, like user data where we're configuring authorized keys. So a lot of different places where these things are set up. On the Kubernetes side, there was some infrastructure overhead in terms of managing our auth workloads. So as I mentioned, DEX and OIDC proxy, we had to run these in all of our Kubernetes clusters. So a little bit of maintenance there, and then the custom tooling around maintaining this internal CLI tool that we use to authenticate to our clusters. So overall, a lot of things that needed to be managed by us that involved internal access. Lastly, how we handled Kubernetes RBAC. So we basically built a custom operator that allowed us to map different levels of permissions to different Okta groups. And this happened on a per namespace level. So basically you could delegate read, developer, operator, and admin permissions, which gave various levels of permission. So hope that painted a little bit of a picture of our previous access setup and some of the pain points that we were facing. And so all of this prompted us to look at teleport as a solution. So I want to walk through our initial teleport setup. I'm going to walk through our root cluster architecture, how we configured our root cluster, and then some of the workloads that we ran to connect to our root cluster. And this part gets in a little bit of details around teleport, so if you're not familiar, I'll try to explain, but there are some teleport technicals here. So the root cluster here, we actually ran this on EC2 as opposed to running this in any Kubernetes cluster that we owned, mostly because we didn't want to couple our access to any specific cluster. Basically, we didn't have any, securely managed clusters that we trusted enough to run this sort of access. So we put it in EC2 just to decouple it from any of our Kubernetes clusters. So we actually used the sample Terraform template, I think, from years ago that Teleport provided us. But basically, what we had was a dedicated VPC for Teleport spread across a couple AZs. Had public and private subnets, and our public subnets, we had load balancers, which we actually used for user access. And I'll talk about this a little bit later because this is one of the things that we ended up changing. But we also ran a Bastion autoscaling group in the public subnet, which we also ended up changing, but we used for basically a jump box to access the proxy and auth nodes in case of any admin operations like TCTL operations that we needed to run on the auth servers. In the private subnets had our proxy and auth, ASGs, and then internal load balancers, which we used to register our nodes with. So I'll maybe talk about the distinction between those load balancers a little bit later, but that was our initial root cluster setup. In terms of storage, we stored our session recordings in S3 and used Dynamo for our backend configuration and audit logs. And for our remote workloads, our Kubernetes workloads, ECS and EC2, we registered these via the internal load balancers over Transit Gateway. So kind of a lot of specifics around our setup, but this is what we went with initially. On the configuration side, we went with Okta SAML auth. So we wanted to leverage a lot of our existing Okta groups that we used for existing access and leverage those with Teleport, specifically for Kubernetes RBAC. So we were able to pass these Okta groups to Kubernetes to maintain the same, I guess, group access that we had before, but just facilitated via Teleport. So we really wanted this Okta auth setup. Another choice we made was to go with static join tokens as opposed to dynamic join tokens. I'm sure there's a lot of discussion around this, but for example, if we went with dynamic join tokens, if you needed to, say, restart a workload or update a workload, you would need to regenerate a new dynamic token. As opposed to going with static tokens, you can just restart your workload and have it automatically connect to Teleport. So this made running some of our remote workloads a lot easier. On the RBAC configuration side within Teleport, we only used a handful of Teleport roles. This just made it simple to configure. We had, say, an engineering role and an admin role. And we stayed away from initially creating lots of specific roles. And the admin roles typically had like SSH access to a lot of our internal nodes, and the engineering role just basically gave access to our Kubernetes setups. So a pretty simple RBAC setup within Teleport. And then the final decision we made here was to configure things manually via the UI, something we ended up changing. But we didn't want to invest time into building a CI/CD setup to apply the cluster configuration during every cluster change. So I guess we traded off some observability into the changes that were made to the cluster for ease of making these changes. A little bit about the remote workloads with our initial Teleport setup. So as I mentioned, EC2, ECS, and Kubernetes. For EC2 access, we installed the Teleport agents on all of our EC2 nodes. We worked with client teams to figure out how best to do this. A lot of times we installed Teleport and user data and had them register at startup time, and had teams configure their own labels so that they could list out their own nodes. On the ECS side, we built a custom Teleport agent image, Docker image that we ran as a daemon set in our ECS clusters. And this allowed us to essentially SSH into all of the nodes in our ECS clusters. Despite them being legacy, we still needed this access. Finally, on the Kubernetes side, we decided to go with initially a leaf or trusted cluster setup. This proved to be a little unnecessary, but initially we thought that this was the best way to go. But with this setup, basically you register all of the nodes in a Kubernetes cluster with a dedicated cluster in that, a dedicated Teleport cluster in that Kubernetes cluster, and then register the leaf back to the root. So it's a little bit of a confusing setup, but that's how we went initially. As I said, we ran our SSH daemon set in each Kubernetes cluster and leveraged Okta auth for RBAC. So this was our initial teleport setup. A couple pain points that we felt after getting things up and running. So the public access bit that I talked about via the public subnets. So we really didn't want to expose both the Bastion that we created for internal node access and those external load balancers. We didn't really want to have those at all. We didn't want users to have to access teleport via the public ALBs. So we wanted to iterate on that design. Again, the leaf cluster setup. So basically the leaf clusters run a proxy and an auth instance in each of your Kubernetes clusters. This was a little overkill for us. We really just needed to connect a Kubernetes agent back to our root cluster. We didn't need the whole proxy auth setup. So the maintenance of those clusters was a little bit more than we needed. On the remote workload side, we didn't have great monitoring and alerting. So we didn't really know when things were going wrong in our remote workloads. So that was one area that we really needed to improve on in our next phase of teleport. And then finally, configuration management. As I said, we were managing configuration via the UI, really not a long-term solution, so we wanted to iterate on that as well. So, some pain points that I mentioned. I want to talk about how we addressed some of those challenges in our V2 implementation of teleport. So, some of the enhancements we made, some of these touch on removing removing external access and moving things internally. So users accessing teleport via the internal load balancers. And then some of these involve configuration changes and then enhancements to teleport. So I'm going to walk through some of these in more detail. So as I mentioned, initially we were deploying a dedicated Bastion in order to access our internal teleport nodes. We really didn't need this, and so we switched from using this internal jump box to basically using a VPN, AWS VPN, connected via transit gateway to our internal teleport VPC. So all access was internal at this point. So we were able to get rid of all of the workloads in our public subnets, and then, as I'll touch on next, get rid of some of our external load balancers. But this simplified our infrastructure deployment, so we were able to get rid of this ASG and also improve security, so no more external workloads. As I mentioned, we moved from our external load balancers to an internal setup. So again, improved our security and leveraged our internal transit gateway setup for accessing our teleport nodes. This was, I guess, a primary change for user access. So as nodes were connecting via the internal load balancers, but users were previously accessing via the public load balancers. So this was primarily a user-driven change. I mentioned before that we initially started with leaf clusters. This was, as I said, a little bit overkill for what we needed. And we ended up switching to using the kube agent setup. So this basically connects your Kubernetes cluster to the root cluster, and you no longer need to connect your SSH agents to this leaf cluster. You can go directly to your root cluster. We also leveraged the public Helm charts for this, so we installed these workloads via open source and, I guess, more trusted Helm charts than our previously forked Helm chart solution. We also changed the way that we registered our nodes with our root cluster. So previously we were registering our nodes directly to the auth servers. This required that we expose these auth servers to basically all of the workloads that we needed to register with our root cluster. We preferred to lock down our auth nodes and only expose our proxy, as that is kind of the mechanism for interacting with teleport. We were able to do that using teleport IoT mode. So basically you can register your nodes via the proxy instead of your auth servers. And effectively, we were able to lock down access to our auth nodes, which was another great security improvement. I mentioned before that we didn't have great observability into our the health of our root cluster and our remote workloads. So one iteration we made was adding internal dashboards and alerts for the health of these workloads. So I guess the most tangible change here was being able to detect when, say, a Kubernetes workload was down. Previously, we didn't really have a good understanding of the health of those remote workloads. So adding this monitoring and alerting really gave us visibility into the health of our systems. So maybe an obvious thing to add, but something we didn't have in our initial setup. This is actually a huge one for us, so simplifying node registration. So previously, as I mentioned, we were using static join tokens to connect our nodes to our root clusters. Teleport supports an EC2 join method, which leverages EC2 instance metadata to connect nodes to the root cluster without needing join tokens. So this improved things in several ways. It made it a lot easier to onboard internal customers to Teleport. If they don't need to manage their own static token secret, they can much more easily onboard their nodes, and the infrastructure setup is a lot easier. This is a little example of what that configuration looks like, but basically you can allow nodes in a specific AWS account to automatically join or authorize these nodes to automatically join your root cluster if they attempt to. So that was a huge improvement for us in terms of node registration. Another change we made was more security oriented. We integrated our teleport audit log Dynamo table with our SIEM setup. So basically we leveraged the DynamoDB table stream to stream our audit logs to our SIEM, basically giving security a little bit more of an ability to process and analyze what's going on in our teleport world. A couple configuration changes that we made on our second iteration. So we moved from configuring our root cluster manually via the UI. We moved to using a Terraform provider, so the Teleport Terraform provider. We built an internal module to basically be able to configure the root cluster how we needed, specifically Okta auth and some of the roles that we were using. So moving away from the UI configuration to Terraform configuration was huge. Another change we made was audit logging to both file on our instances and as well as Dynamo. This allowed us to emit our logs to our internal log processing system, so a little bit better observability into the logging there. And finally, made some tweaks to connection limits. So this is kind of a technical one, but basically we were seeing a lot of issues during workload or root cluster upgrades. So tweaking connection limits in our configuration really improved the stability of Teleport during upgrades. So that was a key one for us. So I wanted to talk a little bit about some of the tools that we use to manage our deployments at DoorDash. So we have used Vault at DoorDash. So Vault is a secrets management solution. And using Vault in conjunction with Teleport has really helped simplify our deployment strategy for Teleport. So basically, we use Vault to manage our static tokens. I mentioned that we use the node, or the EC2 join method for most of our node registration. We do still use some static join tokens, and Vault comes in handy here. So basically, we can inject our static tokens into our Kubernetes workloads so that we don't need to store static join tokens in, say, Kubernetes secrets or some other place where they could be exposed. So this makes, or I guess this allows us to, at startup, retrieve these tokens and easily join nodes to the root cluster. Another tool that we use internally is Spinnaker. So this has really helped with deploying our Kubernetes workloads to all of our Kubernetes clusters. So we have tens of clusters, and it can be a pain to kind of roll these out one by one. Spinnaker has made this process a lot easier with gradual deploys, easier rollbacks, and just more control over how we roll out changes to our clusters. So a little bit about what's next for DoorDash and Teleport. So as was mentioned initially, one of the last remaining access patterns that we need to get rid of is, or need to remove from the Bastion, is database access. So we have been testing out CockroachDB access. We use CockroachDB pretty extensively at DoorDash. So we've been testing out CockroachDB access via Teleport. And this will be one of the last remaining, I guess, major usages of the Bastion so that we can finally remove those. And we're rolling this out to our engineers now. So hopefully we can finally remove our Bastion sometime soon. And one final change that we are looking to make on the Teleport side is migrating our root clusters from an EC2 setup to Kubernetes. So leveraging more of the open source Helm charts for running our root clusters. This will allow us to remove our very custom Terraform setup, which we use to deploy Teleport, and really standardize on the open source tooling that has a lot of effort has been put into. So we'd love to leverage that for our root cluster. Those are our learnings from iterating on our Teleport setup at DoorDash. I want to, if we have some time, open it up to any questions, but thank you.
Thank you so much. That was great. Does anybody have any questions for Luke here? You got one over here?
What can you share about your story around break glass, if there's any issues with Teleport infrastructure?
Yeah, so honestly, our long-term plan is to deprecate the Bastion usages. So I mentioned we historically have used Bastion for internal access. So deprecate all normal Bastion usage, and then keep those around, honestly, as a break glass solution. So because they already have access to these internal systems, keep them around in case Teleport does go down, and then hop onto those and access systems that we need to.
Do you use Teleport to manage access to AWS?
We don't. We don't currently.
Are there any plans?
So we are actually developing another mechanism for that. So no plans now, but as kind of the Teleport ambassador within DoorDash, I'm trying to push for as many use cases as we can. So that might be one that we look for in the future.
Perfect. And then one over here. I think we have time for one more.
What kind of scale are you running on, how many EC2 instances do you have on Teleport?
Yeah, so I guess across our Kubernetes clusters, which are on EC2, and then our just kind of one-off EC2 instances, we're around 5K nodes, probably actually 6K, pushing 7, so mid-thousands, yeah.
And then, okay, I lied. Last one, very last question.
Hey, Luke, this was awesome. Tons of technical detail that I think really helps share with engineers kind of how you deployed, and I think they can abstract the business value from everything that you said in terms of the pain points. Mm-hmm. But a lot of the engineering teams kind of report up to others in the organization that might not understand kind of the value of removing a Bastion host and what that does. If you had to explain kind of the value of your Teleport project a couple layers up in the organization, like how would you encapsulate the value that your team provides by doing all of these things?
Sure. Yeah, I would say that the time saved by the removal of the custom infrastructure that we manage is a huge win. So relying on the out-of-the-box audit logging, RBAC, and just the Teleport system in general allows us to remove so many custom workloads and so much custom infrastructure that the time saved with that is huge. On the other side is the audit logging, which is a huge feature, basically one of the biggest features that drew us to Teleport. So the visibility into, the centralized visibility into any change that happens in our system is huge as well.
Great, thank you so much.
Thanks.
Give it up for Luke one more time.